Good morning. Let's look at section 3.3, logarithmic functions. So let me okay, logarithmic section 3.3, logarithmic, L-O-G-A-R, L-O-G-A-R-I-T-H-M-I-C. Logarithmic functions. Okay, and this is a lesson about inverse. When we talked about inverse functions before, we switched the x and the y, and that gave us the inverse of the function. Well, the logarithmic function is just an inverse. So let's go ahead and get that. Okay, logarithms are the inverse of exponential functions. The logarithm or logarithmic functions are the inverse of exponential functions. So there was really no good way to write the inverse, to switch the x and the y and to solve it. There was no real way to do that. So they just invented something to do that. So this is an example of how that would be written. If I have f of x, here's my exponential function, equals 2 to the x power. Whoops. F of x equals 2 to the x power. The inverse. Remember this notation, f of a -1 there, that is not a power. That means the inverse of that function is going to be log. This is how we write log. We don't write out logarithm every time. It takes too long, right? So log base 2 of x. And so we still use that word 2 for the base. That's the base there. So the logarithm base 2 of x is just the inverse of this. Okay, so let's look at a couple examples of how we might use this. So I could have a problem that says log base 3 of 81. Okay, well, log base 3 of 81. Well, what this is asking is 3 to what power gives you 81. Instead of saying 3 to some power gives you a number, this is the inverse. 3 to what power gives you 81? Well, 3 times 3 is 9. 9 times 3 is 27. And times another 3 is 81. So this is going to be 4. Okay? And another way to read this is log base 3 of 81 equals 4. Or you could say that 3 to the 4th power equals 81. So let me write that as well. That's the fact that I had to use. 3 to the 4th power equals 81. Okay, and you can see this is like an inverse. I'm switching the x and the y. Okay, inverse. I've said inverse about 70 times. I hope that's getting through. This is just an inverse of the functions we've already used. There are a couple special notations that we use. If I just write log of x, log of x without a base there, that means log base 10 of x. So if there's no base there, we assume that it's 10. Okay, there's also natural log. If you look in your calculator, natural log, and we write ln instead of nl because, I don't know why, natural log, ln, it's not nl. That's a special one as well. And you can see right there the base is e. Okay, if there's just the word log, the base assumed is 10. And if you have a natural log, the base assumed is e. So natural log of x is log base e of x. And e is that special number we started talking about the other day. Didn't really get too much into it. Again, I encourage you to go to Khan Academy and watch the videos on that. They are amazing and awesome. And like I said, probably better explained by Sal than I would give justice here. So go ahead and check that out. A couple problems that we could do. We could have log base 5 of 5 to the 4th power. Now note that this base and this base match each other. Okay, I still call that's the base of 2, and that's a base of 2. I still use that word. So these bases are the same. So essentially they're going to cancel out. So my answer is going to be 4. But let me show you how I would figure that out. What I'm asking, let's just say this equals x, equals some number. And what this means, the logarithm means 5 to what power gives me 5 to the fourth. So this is asking 5 to what power gives me 5 to the fourth. Remember, this is an inverse. We switch the x and the y. We're switching these two around. So 5 to the x equals 5 to the fourth. Well, then obviously x has to equal 4 because it's the same base. So x has to equal 4. So if you're given log base 5 of 5 to the fourth, the same base, then your answer is just 4. They cancel each other out. Okay? You could have this the other way as well. Let's say, I'm going to skip a line there because I'm going to have a big exponent here. 3 to the log base 3 of 17. Okay? So instead of writing the log and then the exponent there, I started with 3 to the power of log base 3 of 17. Well, again, this base and this base are going to cancel each other out. So this is just going to give you 17 or whatever that number was there. It could be anything. Okay, there's one other thing I want to look at, the graph of these functions. Let me switch my color back again. So the graph of what a logarithm will look like. Graphing. It sounds like a good enough title. Graphing. And let's say we're graphing the function f of x equals log base b of x. So for any base, the graph is basically going to look the same, and we'll find that every logarithm graph is just a vertical stretch of another logarithm graph. So they're all similar to each other. Okay, there are a couple points that we'll know. The first point is the point 1, 0. Every logarithm graph has this point, the point 1, 0. Well, how come? Well, if you put a 1 here for x, what does this come out to? This is saying, let me make a little note over here. For x equals 1, this will be log base b of 1. This is saying b to what power gives you 1? Well, b to the 0 power gives you 1. Anything to the 0 power gives you 1. So if you put in 1 for x, you always get 0. So that's why we have the point 1, 0. Okay, the next point is going to be, whoops, I covered up my notes here, the point b1. So let's say we have 1 right there. We're going to have another point over here. It's going to be the point b1. Okay, so for x equals b, we'll put in, let's see, log base b of b. This is saying b to what power gives you b? Well, b to the first power gives you b. So you have the point b1. So let's go ahead and graph this. This is what it is going to look like. Okay, you're going to have a vertical asymptote. The y-axis is a vertical asymptote. Okay, the y-axis is a vertical asymptote. A couple other things I want to note using, let's see, limits. The limit, okay, so the limit as x approaches 0, well, it's a vertical asymptote. It's going to go all the way down, and it's not going to reappear over here. It's not like those vertical asymptotes we have with rational functions. It's just going to go down, and it's going to go away. So the limit as the function f, okay, the function f, which is, you know, this function notation just lets me not write this again. It's a little bit neater. As x approaches 0, from the right, okay, it doesn't exist over here, from the right, so from the positive side, is negative infinity. It goes all the way down. One more limit I want to talk about here. The limit of the function as x approaches infinity. Okay, so as x goes off in this direction, what is the graph doing? Well, the graph is going up, and it'll go up forever and ever and ever. It'll go really, really, really slow, but it will go up forever and ever and ever. And there shouldn't be anything written here. I smudged the pen. Apologize for that. So that is just as x approaches infinity, this is going to approach infinity. But really, really, really slowly. Like if this was just log base 10, once I get over to 1,000,000, if x is 1,000,000, the graph will just be up 6. Because, well, 10 to what power gives you 1,000,000? Just 6. So it goes really, really, really slowly up, but it will go up to infinity. There's no place where it will stop. It'll always, you could say, well, when does it get to this point? You can always solve for it. Let me see. So that's one last thing I want to note is my domain. The domain, it has to be greater than 0. The domain x is greater than 0. Okay? And so those are your notes on logarithms.